Okay, so good morning, dear participant. So today, my name is Tosif Diwan, and today I will be delivering on attention and transformer architecture. So we will have a look at like how actually attention works, what is the requirement of attention block, uh, like how it can be considered as a backbone of transformers and large language models that are currently booming nowadays. Basically, we will try to understand all these things with the help of one course, which is this building transformer based NLP applications are there. And you actually, this is nothing but the DLI certification 3. Uh, Here, three parts are there. So first part is this machine learning in NLP. Second part is self supervision, BERT and beyond. And third part is production and deployment. So the first part talks about the attention and all other stuff related to like large language model and transformers, etc. At any point of time, if you are having any doubt or any query, then you can just raise the hand or put your queries in the chat box. We will have the discussion and then we will move ahead. So this is we try to understand this attention block with the help of like example, and we can say the coding stuff also. So basically in left hand side here, you can see three notebooks are there. The first is this transformer block. Then second one is BERT. And third one is about pre-training language model. So in the second session, like today's second session, you will be exploring this BERT and GPT. So in this session, we will explore this transformer architecture in detail. Okay, fine. Yeah, as I have told you that this is nothing but the backbone of all the large language models, transformers, GPT, etc. So basically, this is the stuff that we need to look in terms of various components. First, the various first component is nothing but we will try to understand the basic overview of the transformers. Then second one is nothing but about the tokenizer. Then we will have some concept about embedding. Next, we will try to understand the positional encoding. Then encoder block is there. In that encoder block, self-attention is the layer. Along with the self-attention, multi-head attention is there. Then decoder block is there. And lastly, the visualization. Transformer was introduced in the paper, which was Attention is All You Need. So this was the title of that paper. In that paper, this first time the transformer and attention was introduced by Vaswani in 2017. All these things are in the context of sequence to sequence problem. For example, one sequence is given as input and another sequence is there should be generated as outcome. So we will also look at that why there is a necessity of sequence modeling. For this, we are having some NLP tasks. Just have a look of all these NLP tasks so that you can have the understanding like why there is a necessity of sequence to sequence modeling. These are some of the examples for sequence modeling. First of all, speech recognition is there. So here we can see some input is given to us in the form of audio. For example, this audio is given and we need to just recognize like what was said in that audio. So basically you can consider that this is nothing but the translation from audio to speech or audio to text. These are all called modalities. For example, audio modality, textual modality, visual modalities are there. Okay. Nowadays, mostly data is coming from multimodal side. For example, if we take YouTube video, in that YouTube video, visual modality is there because frames are running, and some, suppose two persons are talking in that video, then it is nothing but some audio modality or speech is also involved into that. And in addition to that, suppose some transcript is running. For example, if you are watching some South movie and some English transcript is there, so that is nothing but the textual modality associated with this. So this type of data is called as multimodal data. Now, question like why there is a necessity of sequence modeling? Because most of the data are there in which we need to incorporate the timestamp. For example, speech recognition is there. So uh, all these audio is there, but there is some timestamp associated with this. For example, what was the audio at timestamp 1? What was the audio at timestamp 2? Like that, this complete is nothing but the sequence. And in some inherent temporal ordering is involved there. Okay. For example, see the outcome, like the quick brown fox jump over the lazy dog. So here also ordering is involved. So first word is the, second word is quick, third word is brown, like that. So temporal ordering is involved over here. Then music generation is there. So input, we should give something, and some other recommendations are played. For example, if you just play one song in Spotify or any other platform, then based upon what you played, some other suggestions are given in the form of recommendation system. So this is music generation. One more NLP task is nothing but sentiment classification. For example, if we say that there is nothing to like in this movie, so here this is the sequence, and here in this sequence, the temporal ordering is involved. For example, what is the first word there? What is the second word is? What is the third word? Nothing, like that. So temporal ordering is involved. Based upon this input, we need to identify which type of sentiment is associated with the input, whether the positive sentiment or negative sentiment or neutral sentiment. Okay. So this is called as sentiment analysis. It is very well known problem. It is not like that that sentiment analysis can be in this example. Sometimes one video is given to us, and based upon that video, we need to recognize this inherent associated sentiment with that video. Next one is DNA sequence analysis is there, which yeah, DNA is made up of sequence of proteins. Okay, so here suppose some input is given to us, and we are interested in finding the DNA. Then machine translation. For example, if we are interested to or any other translation from one language to another language, this problem is solved with the help. By the associated emotions. For example, what could be the various emotions associated with the input? Joy, sorrow, disgust, fear. Okay, all these are here we need to identify, or here we need to extract the associated emotions from that video or from that input. Similar example to emotion detection and sentiment analysis is known as sarcasm detection. For example, some inherent negativity in terms of taunt or in terms of bitter, that sarcasm in that input. So that problem is known as sarcasm detection. For example, if we say that one sentence is there, I like the movie so much that I left in the interval itself. Okay. So here if you look at this sentence broadly, then sentence seems positive that I like the movie so much. But see the second inherent negativity associated with that input. I like the movie so much that I left in the interval itself. So here negativity is associated with the input. We need to identify the associated sarcasm or inherent sarcasm from that input video. This problem or this NLP task is known as sarcasm detection. Another example in which timestamp or temporal ordering is involved here is known as video activity recognition. For example, see here, this is the video and multiple frames are there in that video. Like video is composed of frames, frames at first timestamp, frame at second timestamp, frame at third timestamp, like that. And we need to identify the associated movement or associated activity in that video. For example, if you look at this video closely, then you can visualize that the person which is there in the frames of the video is running. The person is jogging, jumping, standing, sitting. Okay, this is nothing but the various activity that may be there in the video, and we need to process the frames based upon the timestamp, and we need to identify the inherent activity into that video. One more example is there, which is nothing but named entity recognition, in which, for example, this is the input, like yesterday Harry Potter met Hermione. So this type of input is there. In this input, we need to identify the named entity. For example, Harry Potter is nothing but the named entity here. So here we need to identify which are the various named entity. It can be noun, or it can be pronoun, or it can be verb, or anything that we wish to identify or extract. Based upon that, we are having different types of RNN, like how many inputs that we are providing and how many outputs you are generating. For example, this is just a simple RNN cell. So here we can see 1 to 1. So one input is given and one outcome is predicted over here. One to many is that, for example, multiple RNN cell. Here you can see first input is given to this cell, then output is predicted. This predicted output is given as input to the next cell. Then second output is predicted. Second output is given to the subsequent cell, and third output is predicted, like that. This category comes under one to many. Then next one is many to one. Here you can see multiple RNN cells are there. Various inputs are given as input. For example, input at first timestamp, input at second timestamp, input at third timestamp. When all the inputs are given, after providing all the inputs only, we can predict the final prediction. Okay, you can correlate this with sentiment analysis over here. For example, we need to give all this sentence as input. There is nothing to like in this movie. So first word is there, is the second word. There is nothing to like in this movie. This complete input is given as input, and finally sentiment is predicted, whether the sentiment is positive or whether the sentiment is negative or neutral. Then next category is many to many, where multiple inputs are given as input and multiple outputs are predicted. So basically there are two versions of this many to many. First one is this, where multiple inputs are given and at the same timestamp we are having that prediction. Second category is this, when the entire sentence is given as input, then after giving the complete first sentence, we are predicting the second one, or the first word of the second sentence is predicted. For example, machine translation. Look at this. Machine translation comes under this second category, many to many. The entire input is given as input, and the second sentence is predicted after that, one word at a time. Because see, it is not one-to-one relationship. For example, see in this machine translation, this is the first word. It is not directly related to this first word over here, because in each language there is some specific language rules are there. For example, noun after verb, or verb after noun, or verb after proverb. So all these things are there. So it is not one-to-one sort of relationship. We need to first provide the complete input, For example, if we say that English to French conversion, so complete English sentence should be given as input, and then we can predict the French equivalent out. So actually, this was the RNN cell. We are not going in the detail of that. Now we will simply start with the attention block, but just have a look what was the problem with RNN cell. This was the RNN stuff. Okay. This is the current input, and the previous output from the previous cell is coming as, and then we are concatenating both of this. Finally, it is given to some non-linear activation function, and then we are generating this too. Okay. This is the enrolled version of this RNN cell, and this type of sequence are given. For example, sentiment analysis. There is nothing to like in this movie. So the first word there is given as input to first cell, then second word is given, third word is given. After that, we are just finding the final outcome, whether the positive sentiment is associated or negative sentiment is associated or neutral sentiment is associated. There is problem with RNN known as long-term dependency. For example, if very large or if very lengthy sentence is there, in that sentence, suppose word at 50th timestamp, so that may not be very much correlated, or the relationship between the 50th word and the first word may not be easily characterized with the help of RNN cell. So long-term dependency and vanishing gradient problem is there. See here, basically RNN and all the sequence models usage this backpropagation through time. Any neural networks learning algorithm is known as backpropagation or gradient descent. But here timestamp or temporal ordering is involved. So this backpropagation is called as backpropagation through time, BPTT. See, ultimately what is happening here when gradient is getting reduced. See here, if you look at this gradient at 5th timestamp and gradient at 1st timestamp, this gradient is getting reduced. And if the gradient is getting reduced, then parameter will not be updated, because what is the formula in parameter? What is the formula for parameter updation in gradient descent? Parameter is equal to parameter minus learning rate multiplied by gradient. And if that gradient vanishes, the gradient will become 0. So the parameters are not getting updated. If the parameters are not getting updated, then model will stop its learning. So this is the big major problem in this RNN cell. So we have identified two problems. First one is long-term dependency, and second one is vanishing gradient problem. This problem has been addressed in some of the architectural successor, such as long short-term memory and gated recurrent unit, in which they implemented all this stuff with the help of gating mechanism and by providing some memory with the cell. But this also not performing very good, and henceforth we need to move into the attention block, because in all this the very first problem is that the lack of scope of parallelization. For example, if you look at the RNN cell, so first we need to process the input at first timestamp, then we need to process input at second timestamp, then we need to process input at third timestamp, like that. Suppose we are having GPUs, like powerful GPUs are there, and if we wish to process all this input in parallel, so there is a problem over here. Now we will move to the attention block.
Sir, can you explain about back propagation through time equation as well?
Okay, so just let me give you a brief introduction for this. Is it visible?
Yes, sir.
So here these hidden states are there, which are coming from the previous cell, and both of these are given for the calculation of prediction. once we have this prediction like OT minus 1, OT and OT plus 1, on this prediction, we apply some nonlinear activation function. For example, here we are applying softmax. So here we can see the softmax are applied over here. Now we are having loss function. This loss function will calculate the difference between the labeled output and the model prediction. For example, look at this. LT minus 1 is nothing but the loss function which will calculate the difference between this YT minus 1, which is nothing but the actual label, and Y bar T minus 1, which is nothing but the model prediction. So it takes both the input, the actual label and the model prediction, and then just calculate the loss function. Now, why it is called back propagation through time? So in this back propagation, first this error is calculated LT plus 1. This after calculation of this error is back propagated from this timestamp to the very first timestamp. That's why this is called back propagation through time. So this error, any input or any error is back propagated from that timestamp to the very first timestamp. For example, look at this. It was the summarization of back propagation through time. Training algorithm used to provide the first once we have decided the weight and biases. After that, this is the summary. We need to create the network. Once we have created the network, then we just define the loss function. We just define the optimizer. After defining loss function, optimizer, and compiling the model, we will have this third part, which is nothing but a gradient back propagation from the tth timestamp to the very first timestamp. Look at this. W is used in every step up to the output. We need to back propagate gradient from the from the current timestamp through the network all the way to the first timestamp. If you look at this, for example, if this is the input, like what time is it? We just need to predict the output. What time is it? So here we can see gradient is calculated over here. For example, loss function at fifth timestamp is calculated. This gradient is back propagated from fifth timestamp to very first timestamp, but that gradient becomes small and small while getting back propagated from the last timestamp to the very first timestamp. And ultimately, what happens? The fourth step of the backpropagation is nothing but the parameter updation. The general formula for parameter updation is parameters is equal to parameters minus learning rate multiplied by gradient. And if you just see here, when the gradient is getting vanished, so gradient will become zero. So the formula is like that. Parameter is equal to parameter minus learning rate multiplied by zero, because the gradient will become zero. So parameter is not getting updated. And when we say that parameters are not getting updated, it means that model has stopped learning.
Yeah. Thanks, sir. Got it.
Right. Okay, so this was the sequence to sequence model. Now, starting from, it is not like that in 2017 only people come up with the model. Before 2017 also, these are the industries which were producing the various sequence to sequence model. For example, if you look at this in 2014, they presented sequence to sequence learning with neural networks, and it was presented by Google. In that, they have used LSTM as encoder and decoder. So basically, you can summarize that in sequence to sequence model. One encoder would be there. First, we will see the general schematic of this. Yeah, this type of architecture. Sequence to sequence model. It is just an example of English to French translation. So English language is given as input to this encoder block. Encoder performs some calculation, generates the output. This output is given to decoder. Decoder performs some other calculation and finally generating the French equivalent, one word at a time. Okay. So this type of problems are known as sequence to sequence model, in which two blocks are there or two components are there. First component of first working module is encoder, and second block or second working module is decoder. First sentence, we are having sentence pair at the time of model training. For example, when we are training the model, we are having English language as well as we are having its equivalent French language. So English sentence is given as input to this encoder, And finally, this French sentence is generated over here. This comes under sequence to sequence models. So come back over here. In 2014, sequence to sequence learning by neural networks. It was proposed by Google. In that model, it consists of deep LSTM. What do we mean by deep LSTM? In LSTM, we know that gating mechanisms are there, like input gate, forget gate, and output gate. If multiple such layers are there, then that LSTM will be called as deep LSTM. Then in 2015, this NMT stands for Neural Machine Translation. Neural machine translation is nothing but simply machine translation in which we are interested in converting one language to another language. NMT, by jointly learning to align and translate, they have proposed this RNN search model. After that, we are having in 2016 once again neural machine translation, but it was given by Google, so it is called as GNMT. Here a model with deep LSTM network with 8 encoders and 8 decoders using attention and residual connections are presented. Now just have a look. In 2016, they have presented the attention block and residual connection. Actually, this was the actual backbone of attention or transformer. In 2017, they presented this paper. The title of that paper is Attention is All You Need. It was presented by Google. In that paper, actually, they proposed the architecture of the transformer, which was completely based on attention block. Attention was proposed in 2016. In 2017, they presented the transformer block, and the complete backbone of this transformer block was attention mechanism. After that, in 2018, they presented BERT. Full form of BERT is bidirectional encoder representation for transformer. It's a pre-trained model of deep bidirectional transformers. Bidirectional transformer means we are interested in uh, extracting the context from left to right as well as from right to left. So from both the direction we are extracting the context. After that, GPT, Generative Pre-trained Transformer, it was launched by OpenAI in 2018. Now in 19, what is happen? What is happening? GPT-2, the extended version of GPT was launched once again by OpenAI. Then larger model of transformer. The size is Transformer XL. It was produced by CMU and Google Brain. Roberta is once again some variant of BERT, which is called as robust BERT by Facebook AI. Then some other architectures which are already some variant of BERT and other mega architectures such as IRNI 2.0 by Baidu, then Megatron LM by NVIDIA. All these are presented in 2019. In 2020, Microsoft launched Turing NLG, which is nothing but neural language generation. And in GPT, what is happening? The extended version of GPT, which is nothing but GPT-3, is launched by OpenAI. Now, uh, first of all, we need to establish the differences between the traditional stuff. Traditional stuff means CNN, RNN, and the attention and transformer block. The first difference between traditional model such as CNN, RNN and attention block is that in CNN, RNN, they are actually very compute intensive model. Okay. Second difference is that there is very less scope of parallel processing in CNN or RNN. However, this is not the case with attention or transformer block. In attention or transformer block, very few steps are there which needs to be done in sequential manner. Otherwise, rest of the all other operations can be done in parallel. Thing is that we are having very powerful GPU or powerful workstation. We are having programming languages such as CUDA, OpenAI, MPI. All these are parallel programming languages. Now, when we are having enough compute power, when we are having parallel programming languages, and why not to process all these things in parallel if they are not having any dependency on each other? So this was the actual logic. So attention got this popularity due to these two reasons. First one, the traditional architecture were very compute intensive, and second one, there is very less scope of parallel processing in those traditional architecture. Once again we try once again we start our journey by understanding or by learning sequence to sequence model. So this was the stuff: encoder decoder. In encoder we are giving input, and from decoder we are generating the output.
Sir, each token or each word is calculated or processed parallelly, or each sentence is processed parallelly here in encoder decoder.
Each token is processed.
Okay.
We will see all these things when we will try to understand the tokenization, which is there.
Okay, sure. Thanks.
So let me just explain this. This entire diagram is visible. See here.
Yes, sir.
Now, just look at this encoder and decoder. Here we don't know like what is there inside encoder, what is there inside decoder. They are just treated as the black box. Now, it is just a elaborative schematic of encoder and decoder. Here, see what is there inside encoder and what is there inside decoder. For example, look at this. This is my encoder. In encoder, first of all, some input. We are having this input. This is called unprocessed text. Okay. Now, what is that? For example, if this was the input, I am a student. So this input is given over here. I am a student. This input, I am a student, is given to tokenizer. Tokenizer tokenizes the input. What do we mean by that? Tokenizer tokenizes. I will become the first token, M will become the second token, A will become third token, and student will become the fourth token. Once this input is processed by this tokenizer, once this input is processed by the tokenizer, then we are having embedding. What is embedding? Embedding means we need to represent all these tokens into some predefined dimensionality. For example, if we say that we are having some predefined dimensionality 100, okay, so we need to embed each of these tokens into that 100 dimensional space. It is nothing but the distributed representation of the input. For example, I, this first word I is represented as 100 dimensional vector. Second word M is represented as 100 dimensional vector. Third word A is represented as 100 dimensional vector. And the fourth word student is also represented as 100 dimensional vector. It is called distributed representation. What do we mean by that? Uh, now just give me 1 second. Okay. So, no, actually, I was not saying something. I was just searching this. Distributed representation of the word or of the token is like that. For example, here, if you look at that, there should be some logic behind the representation. For example, if we say that the difference between king and queen should be same as the difference between man and woman. But here, what is the difference between king, queen, and man and woman? There is some royalty factor associated with king and queen. Okay, so distributed representation indicate that at some place we give points to royalty. At some place we give points to like gender. At some place we give points to some other stuff. It is called distributed sort of representation. This one. It is called embedding. I hope that it is clear now. In left hand side, it is nothing but word. So these are the words: cat, kitten, dog, house, man, woman, king, and queen. Okay. Now we have defined that this word should be represented in a seven-dimensional space. Okay. These words are represented in seven-dimensional space. Look at this. This is the first vector. How many entries are there? Seven. So this is seven-dimensional space. Similarly, kitten, dog, house, man, woman, all these are represented with the help of seven-dimensional space. On each of these dimension, for example, some point is associated. For example, the first entry related to living being. Okay, living. For example, look at this house. House, is it living being? No. So here we can see some very less values there. For example, minus 0.0, minus 0.8. So it is not very associated with living being. For example, dog is there. Dog is there. So like feline. If you look at that, dog, feline. So negative entry is there, but kitten, it is positive entry. Cat is once again feline. So 0.9. Okay. On the other hand, if you look at that royalty, look at this fifth one. Royalty is one attribute. So if you look at this royalty, just look at this man, woman, king, and queen. Men and women are not very not related with some royalty, very less royalty because they are simply normal man and normal woman. No royalty is associated. If no royalty is associated, then this value is very closer to zero. For example, minus zero point 0.1 and zero point 0.1. However, the other two stuff, which is nothing but king and queen, with both of this king and queen, some royalty is associated over here. So see here, king 0.9 is the royalty factor and queen 0.8 is the royalty factor. Lastly, visualization. This seven-dimensional space can be represented with the help of some lower dimensionality so that we can understand the difference or a representation is fine or not. For example, look at this. Difference between man and woman is same as the difference between king and queen, so that you can perform some embedding arithmetic on this. Embedding arithmetic on this. What should be arithmetic embedding? For example, subtract if you subtract royalty from king, then you should get man vector. I am repeating this sentence. If you subtract royalty from king, then we should get man vector. I hope that thing is clear. Okay. What do we mean by positional encoding? Look at this. What is the position of I? Position of I. Okay. So we were understanding this third thing, which is nothing but positional encoding. Positional encoding stands for, see, in CNN, RNN, we were specifically providing some positional information about the words. Okay. But here in attention mechanism, we are not providing any positional information. So the thing is that we need to give some additional input in terms of position. So we need to give some additional inputs in terms of positional encoding. Now, if you look at this input embedding, so this input embedding and positional encoding are first added. Now, if we had decided that input embedding should be represented by 100-dimensional vector, so the size of this positional encoding should also be 100. After that, what will happen? This positional encoding size of 100-dimensional vector is added with this input embedding, which is once again 100-dimensional vector. So this 100-dimensional vector is added with another 100-dimensional vector. inherently, ultimately, what we are doing, we are providing or we are ingesting positional information in the input. Okay. So these are the things that we need to understand. First, we will try to understand this tokenizer. The task of tokenizer is to tokenize the input. Embedding layers. There are various standard embedding algorithms are there, such as word to vec, which can be implemented with the help of continuous bag of word or skip gram. Then fast text is there, and global vector is there. Third thing is positional encoding. So we need to input some positional information about the words. Then multi-head attention, mask multi-head attention, and some other components are there. In the original paper, that they presented in 2016, in which 6 identical layers were there for encoder and 6 identical layers were there for decoder. 6 layers for encoder and 6 layers for decoder, right? So this is one encoder. After that, second encoder number 2 would be there, then encoder number 3, encoder number 4, encoder number 5, like that. Similarly, 6 decoders are there. Now we will try to understand this tokenization. Tokenization basically the numerical representation of the input. We are having the vocabulary. We just see whether the token or whether the word is present in the vocabulary or not. For example, see this. I am a student. So I am having one vocabulary. We will check whether the first word I is present or not. If it is present, then we will have some numerical representation. For example, at what place or at which position the word I is present there. Similarly, M is there. M, whether the M is present in the vocabulary or not. If it is present, then what is the location for this or what is the position for this? It can be represented with the help of one hot encoding. What do you mean by one hot encoding? For example, the student, this student word is present at 10th position or 10th place. So suppose we decide that this should be represented in a 100-dimensional space, then in that 100-dimensional space, all the entries will be 0 and only the 10th entry will be 1 because student is placed at 10th position in the vocabulary. So after tokenization, we will have embeddings. Now, what do we mean by embedding and how can we convert or how can we get the embedding? So for this, we should have some embedding matrix. Size of that embedding matrix is this. Vocabulary size multiplied by D model. Once we have one hot vector of all these tokens, once we have, look at this. Once we have one hot vector of all these tokens after tokenizer, this one hot vector is multiplied to that embedding matrix. This one hot vector is multiplied to embedding matrix. Size of that embedding matrix is what? Size of that embedding matrix is vocabulary size multiplied by D model. And what is the size of this vector after tokenizer? After tokenizer, the size of this model is vocabulary size. For example, if we are having 10,000 words in the vocabulary, okay, then 10,000 word, like 10,000 dimensional vector would be there, 10,000 values would be there. So that will become 1 multiplied by 10,000. And second will be having one matrix. The size of that matrix is 10,000 multiplied by D model. And what is that D model? D model specifies that we are interested in defining the embedding in 100 dimensional, in 200 dimensional, in 500 dimensional, like that. So if we have decided that the word should be represented after embedding in 100 dimensional space, then that will become 100. D model will become 100. So this vector after tokenization is multiplied to that embedding matrix. Our ultimate aim from learning is to learn that embedding matrix. Once we have learned what is the final result or what is the final entry in that embedding matrix, then we can generate the embedding for each of these tokens. Once we have embedding matrix, we should have or we can have all the embeddings for all such tokens. Look at this. A D model is 512 in the original transformer that they presented in the paper. but it can be transformer big also, in which D model is 1024. So this is nothing but dimensionality. This is nothing but dimensionality. Like which dimensionality? This one. Here we can see the dimensionality is 7, because here this is just an example. We decided that this word should be represented in a 7-dimensional space. Similarly, here what we are doing, here we are defining that this dimensionality should be 512. All such tokens should be represented distributionally in a 512 dimensional space. Similarly, the larger version of transformer is nothing but transformer big, in which the D model is 1024. After that, we are having positional encoding. Positional encoding tells about the position of the words. For example, first position, second position, third position, like that. So these are nothing but the various positions. It can be implemented as alternate sine and cosine functions. So we are not going in the details of this. The basic aim that here is to understand the encoder block. Any doubt or any query till this point? Okay, so let us continue with the transformer encoder. Now from here, yeah, we need to understand the various working modality of all the encoder blocks. It's very interesting. See here, in the original paper, 6 identical layers were there and 12 total layers are there. So 6 encoder layer and 6 decoder layers are there. In each of this encoder layer, we have multi-head self-attention mechanism. And second one is very simple, which is nothing but position-wise fully connected feed-forward networks. This is the structure of one. This is the structure of one encoder block. We will try to understand the entire calculation with the help of this block only. Now this should be interactive. You can also answer the questions. What is the input given to us? Input is this tennis ball. Okay. What is the first word? First word is tennis and second one is ball. What is the first and foremost step? First step is tokenization. First, I will check whether the word tennis is present in the vocabulary or not. If it is present in the vocabulary, then we will just have the representation, one hot representation of this tennis. Similarly, I will check whether the ball is available in the vocabulary or not. If it is available, then I will check the representation. I will check the implementation. I will check the representation of ball. Once we have tokenized representation of tennis and tokenized representation of ball, after that, we should identify the embedding, or we should find out the embeddings. Like what is the embedding for tennis and what is the embedding for ball. Here we have to decide like under what dimensionality we are interested in defining tennis, and in what dimensionality we are interested in defining ball. Okay. So this is my embedding. You can use any standard algorithm such as word2vec, glow, fast text, or any other algorithm. Once we have this embedding vectors, embedding vector for tennis and embedding vector for ball, after that we should have positional information vector. So then positional encoding of tennis is there and positional encoding of ball is there. Size of this vector and size of embedding vector is exactly same. Size of this positional encoding vector and size of embedding vectors are exactly same, because we are just adding both of these vectors. Ultimately, we are ingesting the positional information into the input. So like that, tennis is nothing but the first word and second ball is nothing but the second word. Yeah, both the word will be given as input simultaneously. Both the word will be given as input simultaneously. Now, one vector representation is there after tokenization, after embedding, after positional encoding. One final vector representation for tennis and one final vector representation for ball. Till this point, is it any doubt or any query? After tokenization, embedding, and positional encoding, we are having one final representation for tennis and we are having one final representation for ball.
Sir,
Now,
if we have a large sentence, then all the words are given simultaneously, or two, three, or there is some count that is given simultaneously.
no, no, all the words are given simultaneously.
Okay. Thanks, sir.
Fine. After that, what is attention? First, we will try to understand the intuition behind attention. From this diagram, I hope the things are clear. So the sentence is given to us. What is that sentence? My dog loves playing fetch with a tennis ball. Okay. In this entire sentence, we need to consider each and every pair. We need to consider each and every pair of input. And if the words, or if the words are related to each other, then it should reflect a high attention score. And if the words are not related to each other, then they should reflect a low attention score. So this is what ultimate intuition behind it. If you look at this, like playing and ball, they are related to each other, so they should reflect high attention score. However, second pair, tennis and ball, they are also related and closely occur each other, so tennis and ball should reflect a high attention score. But if you look at that, dog and tennis are not related to each other. Actually, they are loosely related, so they should reflect a low attention score. For example, we should identify the attention score for every such pair. Is it fine? Now, how to calculate this attention score? Attention mechanism in the transformer is composed of three components, where we are having three representations. First one is query representation, key representation, and third one is value representation. Okay. So far, where we have reached, we are having one final vector representation for tennis. We are having one final vector representation for ball. From this one final representation of tennis, we should generate three more representations for tennis. Those three representations would be query representation for tennis, key representation for tennis, and value representation for tennis. Similarly, the second category, in which ball is there, from this final representation of ball, we should generate three representation for ball, which are query representation for ball, key representation for ball, and value representation for ball. How we will generate these representations from that final representations? For that, we should have one matrix. First matrix is responsible for generating query representation. Second matrix responsible for generating key representation, and third representation or third matrix responsible for generating the value representation. Okay. With the help of backpropagation or gradient descent learning mechanism, we need to learn these matrices. We need to learn these matrices. Okay. Once we have these representations, like query, key, and value representation for tennis, and query, key, and value representation for ball. Okay. Once we are having both the query, key, and value representation for tennis and ball, after that, this is nothing but the attention that we need to perform. Okay. Look at this once again. Do not confuse. Once we are here at this point, we have one representation for tennis. From that one representation, we will generate three more representation. So far, we have not given these things to self-attention. From this single representation, we generate three more representations. Three representation for tennis and three representation for ball. These three representations, like query, key, and value representation for tennis and query, key, and value representation for ball, are given as input to self-attention. And what is happening in this self-attention? In this self-attention, first of all, we are multiplying query by key. Query by key, it is nothing but the transpose of key. Okay. So for example, if all these vectors are 100 dimensional vector, so 1 cross 100 is multiplied by 100 cross 1, and this is nothing but square root of dk, which is there in the denominator, is used for some sort of normalization, because we do not want to operate upon very much large. And after that, we take the softmax of this, and finally this entire stuff is multiplied by that value representation. So can we call this attention of query key and value representation to this weighted representation of value? Yes, absolutely yes. What we will do, see here. Look at this small q, k, and v. Small q1 is nothing but query representation for tennis, k1 key representation for tennis, and v1 value representation for tennis. Similarly, we should have q2, k2, and v2. Okay. For all these pairs, we should multiply q1 by k1, like query 1 is multiplied by all the keys. Similarly, second query is multiplied by all the keys, like that. So all these things are nothing but in terms of individual calculation. Can we do all these things in terms of matrix multiplication or parallel calculation? Yes. So far, how many inputs are there? 2. So this is my query matrix. So this first row indicate first row of capital Q. First row of Q indicate query representation for tennis. Second row of Q represent query representation of ball. Similarly, this is the transpose of K. So first column indicate key representation for tennis and second column indicate key representation for ball. I hope that the things are clear. So this 2 cross 3 matrix is multiplied by 3 cross 2 matrix. The resultant would be 2 cross 2 matrix. It is nothing but matrix matrix multiplication. After that, in denominator, we are having square root of dk, and finally we are taking softmax of this. The entire stuff is multiplied by this V. This V matrix is there. First row of V is nothing but value representation of tennis, and second row of V is nothing but value representation for ball. Okay. Finally, we are generating this Z. This Z is nothing but outcome of attention. This Z is nothing but outcome of attention. First row indicate final summarized representation of tennis. Second row represent final summarized representation of ball. And if you look at this closely, in this first representation, surrounding words or neighboring words are also taken care into consideration because we are multiplying query by key. So the first representation, like query representation of tennis, is multiplied by key representation of tennis. Similarly, query representation of tennis is multiplied by key representation of ball. So one query representation is multiplied by all key representation. Similarly, second query representation is multiplied by all key representations. All together, we can say that all query representations are multiplied by all key representations. This process, this is called attention. This is called attention formula. Attention formula, what is the input? Query key and value. Query key and value, these are the input, and final outcome is Z. Next, multi-head attention. So far, we have understanding that only single head is sufficient, but it is not the case. For example, look at this. Look at this input.
Sir,
With the tennis ball.
attention.
Yes, please.
So the self-attention score that's calculated, so QKV is multiplied only one time to get the final value, or like in neural networks, we calculate it and optimize somehow?
No, it is multiplied for all the values. Now, for example, this is the entire sentence. For each of this sentence, we should have 3 representation. For example, dog is there. For dog, I should have all these 3 representation, query, key, and value. For tennis also, I should have all these 3 representations. And lastly, when I'm having all these representations, finally, it's given to this block, right? And this block is generating this Z. So just look at this. What should be the dimensionality of Z? How many terms are there? 1, 2, 3, 4, 8, 9. Okay. So in this Z, this time 9 rows would be there. First row represent what? the final representation of my, second row represent final summarized representation of dog, third final summarized representation of laws, like that. Here in this final summarized representation, they are also taking care of the surrounding words, because if you look at that operation,
Mhm.
queries are multiplied by keys. All queries are multiplied by all keys.
Okay.
Like, is it fine, or still
Sir,
there are some confusion?
yeah, so I have said little confusion. So it is single time multiplication. Suppose I have one word tennis, one word dog, one token tennis, one token dog. So for each token, this softmax operation will be done only once, or it will be somehow like in neural network, different layers. We optimize, we go through multiple times, correct? Back propagation, forward propagation, something like that will happen. Or only
No,
one
no, no.
single time.
It is one time activity.
Okay, got it. Thank you, sir.
Sir, small clarification.
Actually, in the second session, I will ask madam to like to do the implementation for this also.
Okay,
Like,
right.
when you implement this, then I think some of the queries would be resolved there also.
Sure. Thanks, sir.
Sir,
Yes, please.
hello. Sir, a small clarification, sir. Please correct me if I'm wrong in my understanding.
Uh,
So you have
can
created
you
about
please be a little bit louder?
We have created the representations query key value, and we are multiplying of all the tokens, and we are multiplying using matrices at one single time, right? Just a single operation, matrix operation. That's it, no, sir?
Yes.
Okay. Yes, sir. Thank you.
Now, next one is multi-head attention. Why there is a necessity of multi-head attention? For example, look at this input. This input. In this input, suppose there might be different aspect in the input. For looking at some different aspect, we may require one attention mechanism. For looking at some different aspect in the input, we may require some different attention. That's why there is a requirement of multi-head attention. In the original paper that they presented in 2017, in which eight such heads were there. So this is called multi-head attention. So for one head, one query key value representation is there. Likewise, for second head, another query key value representation would be there. For third head, third time query key value representation would be there, like that. So if eight such heads are there, then eight such query key value representations would be there. This is called multi-head attention. And the logic is pretty simple, because one head may not be looking upon all the aspect of the input. That's why we require multiple such heads. Next one is nothing but the decoder side. Now we will try to understand the decoder, what is happening in decoder. See, this was the architecture. Input data tokenization, then input embedding, then positional encoding. After that, this multi-head attention, and here we can see some residual skip connections are also there. For example, the input which is given to multi-head attention, it is also given to the add and norm for the subsequent layer, because we suppose some gradients are getting vanished there. So we want that information should be flown from input to output. That's why some residual or skip connections are there. This is very simple plain neural network of feed forward network. We can say that it is dense or fully connected neural network, in which one neuron is connected to all the neurons of the previous layer. This is one layer. Finally, after that, we generate the outcome of this. This is the encoder number 0. This encoder number 0 output is given as input to the subsequent encoder, that is encoder number 1. Then output of that encoder is given to the subsequent encoder as input, like that. Most of the things are same for decoders. What is there in decoder? Outputs is there in decoder, because at the time of model training, we are having input and output both. For example, English sentence is as input, and this is nothing but my output sentence. Both the sentence are given as output. So this output is shifted one position right, and this output is shifted one position right. And outputs are predicted one output at a time. For example, look at this. When I'm predicting this first word, then all these tokens are masked. Okay, all these tokens are masked because we do not want that information should be flown in the model. So for at first timestamp, this word is predicted. This predicted word is given as input to the subsequent cell. Then second word is predicted. Then third word is predicted. This prediction is happening one token at a time. This is nothing but the sequential generation of the outcome. So this is my output embedding. This is my output embeddings. Once again, positional encoding is involved over here. You can see this multi-head attention. And this is also multi-head attention. Now you can see here two multi-head attentions are there. In multi-head attention, if you remember that in attention mechanism, how many inputs are given? 3 inputs: query, key, and value representation. Okay. So if you look at this masked multi-head attention, this masked multi-head attention will be there in case of model training only. In case of model training only, yeah, as I have told you that when I am predicting the first word, then from first word to fourth words, all the words are masked because it is very illogical that we are predicting the first word and we are giving this word as input to the model. Okay, all these 4 words will be masked. When I'm predicting this fourth word, which is nothing but this student. So first, second, third word are given to the model, but the fourth word is masked. So at any point in time, if I am predicting suppose 10th word, so from 10th word onwards, all the words are masked. From first word to ninth word, these are given as input to the model. This property where we want that information should not be flown in the leftward direction. This property in which we first or we consider the previously generated word into consideration and all other subsequent words are masked. This property is called as autoregressive property. This property is called as autoregressive property. What is autoregressive property? First word is predicted, then first word is given as input to the model. Second word is predicted, then first and second both the words are given as input to the model, but third and fourth are not. When third word is predicted, first, second is given as to the model, third and fourth are not given. When fourth is predicted, so 1, 2, 3 are given to the model, but fourth is masked. So this property is known as autoregressive property. Now, if you look at this closely, in masked multi-head attention, query, key, and value. See here, in this block, 3 inputs are there: query, key, and value. All these 3 inputs are coming from downward. Okay. But if you look at that another multi-head attention, which is there in this decoder side, this multi-head attention, in which 3 inputs are there. So 2 input, query and key. 2 inputs, query and key, are coming from the encoder side, and only value is coming from the previous one. Okay. This attention mechanism in which 2 blocks or 2 input, which are the query representation and key representations, are coming from the encoder side, and only value vector is there which is coming from the previous layer. This type of attention is called cross attention. This type of attention is called cross attention.
Sorry, sir. Can you explain cross attention once again, please?
Yes. See here. If you remember that attention block, how many inputs are there in that attention? 3.
QKB, yeah, 3.
Query key value, and final outcome is Z.
Yeah.
Fine. So if you look at this masked multi-head attention, so these are the 3 inputs: query, key, and value. All these 3 inputs are coming from the downward.
Yes.
If you look at this second attention, which is multi-head attention, in which 3 inputs are there. In every attention, 3 inputs are there. First two input, which is nothing but query and key. Query and key are coming from encoder side, and only value is coming from the downward side.
Okay.
This type of attention is called cross attention.
Okay.
See here, encoder number 0 is there. This encoder number 0 output is given to encoder number 1, then encoder number 2, encoder number 3, like that. And after that, the final outcome of the last encoder, two things like query and key, which are given to attention of decoder side, and final value is given to the subsequent downstream block. This is called cross attention mechanism.
Sir, this is used for translation or this is used for generation of new text like ChatGPT? Yes, or both?
This is used for correlation from input to output.
Okay. So can be used in both in translation and in new text generation
Yes,
instead?
it can be used in both.
Okay, great. Thank you, sir.
So far we have seen self-attention. Then this was matrix multiplication, mask multi-head attention. It was decoder. I hope that this picture is clear. What is the input? Tennis ball. This is encoder number 0. Self-attention, head and norm, feed forward. This is encoder number 0. After that, this output is generated. It is given to encoder number 1. Then output is given to encoder number 2, 3, 4, 5, like that. See the outcome of fifth encoder. Outcome of fifth encoder is given to all the decoders. In the original paper, how many encoders are there? 6. How many decoders are there? 6. Okay. So if you recall this attention is called as cross attention. Why cross attention? Because some of the stuff are coming from encoder, some of the stuff are coming from the decoder. Is it fine? Encoder decoder attention is called self attention. Some of the stuff like query and key are coming from encoder side, but from which encoder number? Encoder number 5th. So encoder number 5th is giving query and key to decoder number 0, to decoder number 1, decoder number 2, up to all the decoders. I hope that the things are clear.
Yes, sir.
Now this is mask multi-head attention, and finally this is the visualization. From this visualization, the things would get clear to you. Here we are just calculating like neighboring values, then query key and value representations. So how one word is related to another word, and finally generating the first word. This is the first word is generated. When first word is generated is given as input to the subsequent, and then second word is predicted. After predicting first and second word, third word is predicted. So one word at a time is predicted. This property is called as autoregressive property. Okay, so this was the transformer one. Now we will have a look at some of the important stuff of BERT. BERT will be covered in detail in the second session.
Sir, one question.
Yes, please.
Sir, we are processing everything in parallel. So
Yes.
first word, second word, last word, their output will be coming all together at once, correct?
No. They are generated sequentially. See, in this entire stuff, not all the things are done in parallel.
Okay.
If you look at this self-attention things, so it can be done in parallel because everything is independent of each other. But while generating the outcome, one word is generated at a time. When first word is generated, after that only second word is generated. It is not possible to generate both the words at the same time.
Okay. Only input is parallel.
Only input is parallel, and some of the calculations are there in decoder side which can be done in parallel.
Okay.
But outcomes are generated sequentially.
Okay. Got it. Thank you.
Okay, so next one we will see the BERT. We will just have a look at the BERT and then we'll stop. Now we are having session on 12th. So on 12th, I will be sharing the event code with you. This is nothing but the DLI workshop 3. So then you can also use, or you can also access all these notebooks, all these like presentations, everything you can access after that. So in this notebook, we need to understand that language model with Nemo. These are the word piece tokenizer. Every model has some tokenizer. These are the broader category of tokenizer: character level, word level, or subword level tokenizer. Then we are having word piece algorithm. After that, we will have tokenization with Nemo, and then some exercise is there, followed by contextualized word embedding is there, and then attention mechanism is there. I think one message is there. So once a token is generated, the processing or start all over to generate the next token. In the decoder side, it will start again once again, because input is completely processed. In decoder side, the things will get start once again, will be starting once again. Only that masking part is a little bit tricky to understand. First word is generated, then it is unmasked. Second word is generated or second word is predicted, then it is unmasked, like that. Fine. So this is about the bird. What is the difference between previous architecture and this architecture? What is the difference that you observe over here?
Lesser layers.
No, actually, in the previous architecture, both parts are there, encoder and decoder. But in BERT, decoder part is not there. No decoder is there. Only encoders are there. Just okay. So when I'm talking about BERT, so here no decoder is there. Only encoder is there. Now, what is the full form of BERT? Bidirectional encoder representation for transformer. Only encoders are there. For example, just imagine that 10 encoder blocks are there and we are having input. So we are having that complete input. For example, this is the input given to us. This is the input given to us. This input is given to 10 encoder blocks, encoder number 0 to encoder number 9. And finally, the outcome of this, which is nothing but the outcome of encoder number 9, is nothing but the very richer representation of the input. Very rich representation of the input. When we are having very rich representation of this entire sentence, then we can use this richer representation in our downstream task. It can be sentiment analysis, it can be emotion detection, or it can be any other task. The thing is that when we are having richer representation or when we are having efficient representation of the input, then definitely the model will perform good. Okay, so BERT is just like that, yet another feature extractor. For example, when BERT2 is used for vector embedding, GLOW is used for vector embedding. Similarly, BERT is used for that another like vector representations. It is used for effective representations. It is trained on two loss function. One is that masked language model and second one is next sentence prediction. What do we mean by that? See here, suppose if this is the sentence, in this sentence we masked some of the stuff. For example, if I just mask this language, or if I mask some other word that is encoder. See, I myself is masking the word, and our task is to predict that masked word. Yeah, this is a very good question. Like when to use encode. I'm just coming to that. Okay, so first we will understand this masked language model prediction and next sentence prediction. So here, mm, these words are masked. Once these words are masked, then with the help of BERT, we train the model such that masked words are predicted. This will become the first loss function, masked language model prediction. Now second one is next sentence prediction. What is next sentence prediction? In next sentence prediction, we give pair of inputs, a pair of sentences. For example, this is the first sentence, and then this is the second sentence. Both the sentences are given as input. Both the sentences are given as input. When these two sentences are adjacent to each other, then outcome is 1. And when these sentences are not adjacent to each other, for example, I am taking first sentence from here and second sentence from here. Okay, so they are not adjacent to each other, then the outcome should be 0. So I am just modeling this problem as classification problem. When sentences are adjacent to each other, then word one is predicted as like one is considered as outcome, and when they are not adjacent, then 0 is considered. So this loss function is nothing but the second loss function on which my BERT is trained. It is known as NSP, next sentence prediction. So we are having this Nemo toolkit. So we are not going in the details of this. Just run this cell. So in BERT, we are having two types of implementation. First one is known as BERT base uncased, and second one is known as BERT large uncased. In the first one, we are having 12 transformer block. In the second one, we are having 24 transform. But which transformer blocks? Encoders. Only encoders are there because decoder is not there. Okay. So only 12 transformer blocks are there. And how many parameters are there? 110 million parameters are there in basic, and 340 million parameters are there in larger version. So this is nothing but the pre-trained model name. Here we are using that BERT base uncased, and this model is extracted from here. Now, once this model is downloaded, from this model, we need to just identify or understand these things. So far, we have understood the complete transformer architecture. We have seen that query key value representation and all other stuff. Now we have the model. Which model? The base model, like BERT base uncased. We have this model. Now from this model is stored in this variable model. So I'm just running this model and I will try to correlate all these things. We need to identify whether how many layers are there, how many transformer layers does BERT have, how big is my hidden layer size, can you identify query key and value matrix, can you identify two loss component, one responsible for next NSP, next sentence prediction, and another one is for masked language model, MLM. So just run this model. When I am running this model, now look at this outcome. Now you tell me whether you can correlate this BERT architecture with this architecture. This one. You remember that? First tokenization, then embedding, then positional encoding, then multi-head attention, add norm, feed forward, and all these things are there. Look at this now.
So token type embedding is something different here, right?
Yeah, token type embedding is something different. Basically, so far we have seen that positional encoding and word encoding. Token type embedding is that, for example, if we are giving two sentences, because we are in NSP, we are giving two sentences, next sentence prediction.
Yes, yes.
If sentence belongs to, or if token belongs to first, And if token belongs to second sentence, based upon that, we are having token type embedding. That's why here you can see 2 is there.
Okay.
Okay, fine. Now see, this is the BERT language model. Now first, this is my encoder. Encoder is getting started. After encoder is getting started, what is the first layer? This embedding is there. Which type of embedding? First, word embedding. What is the size of this word embedding? This is nothing but the dimension of that word embedding. Embedding matrix 30,522. These many tokens are there. 768 is nothing but dimensionality in which I am interested in defining that token. After that, positional encoding is there. So 512 multiplied by 768. See here, word embedding is generating vector of size 768. Similarly, positional embedding is generating vector of size 768. These two vectors are added. Once again, we are having one more embedding, which is nothing but token type embedding. Once again, the size of this vector is 768. All these three are added. Okay. After that, my first encoder is getting started. After that, encoder is getting started. This is my encoder. Okay. In that encoder, total how many encoder layers are there? If you see here, these are the two BERT model. This is what I am exploring. How many transformer blocks are there? 12 transformer blocks. Go here. This is nothing but the first transformer block. From where it is starting and where it is terminating. Look at this till this point. This is my first encoder or first encoder block. Look at this. What is there in the first encoder block? First, I am having self-attention. Now I will try to understand self-attention. See, this is my first one. Attention block is there. In that attention, I need to define first query key and value matrix. So these are the query key and value matrix. 768 by 768 dimensional matrix is there. From this query key and value representation, I need to generate Z. This is nothing but the outcome. This is nothing but the outcome. Input feature and output features. This outcome is nothing but the outcome of self-attention. Right? After that, add and normalization is there. So here we can see layer normalization is nothing but this add and normalization. After that, we are having feed forward network. So this is my intermediate result. This is my intermediate layer. It is nothing but feed forward layers are there. And this is the outcome of feed forward layer. See here, feed forward layer, and this is the outcome of feed forward layer. I hope that the things are clear. Like you can just correlate this, not to worry about the specific entries. But I hope that this is clear. First one is this attention. Query key value matrix is there. It is given as input and finally Z is generated. This Z is nothing but this output. After that, we are having fully connected layer. So this is my intermediate fully connected layer. And once again, the outcome of this is this. So this is encoder number 0. This is nothing but encoder number 0. After this, same repetition here. Now it is nothing but encoder number 1. Look at this. From here, encoder number 1 is getting started. And how many such encoders are there in BERT base uncased? How many encoders are there? 12. Encoder number 1, then encoder number 2, encoder number 3, 4, 5, 6. Exactly same architecture is there. 9, 10, up to what? Up to 11. Why up to 11? Because numbering is started from 0. So this is 0 to 11. So total 12 encoder blocks are there. After 12 encoder blocks, we should have a loss function. So here we have defined this MLM classifier. MLM stands for masked language model. This is MLM classifier. And here we are having one more loss function, which is nothing but NSP classifier, which is next sentence prediction. So we are having two loss function like MLM loss and NSP loss. So we are having the cross entropy loss for both of these and then aggregate loss. I hope that the things are a little bit relevant. Now here we can also predict total how many weights are there. What do we mean by weights? Weights are nothing but the parameters, like weight and biases are there. So here we can also print total number of weights. So these many weights are there. It is nothing but 110 million parameters are associated. So these are nothing but the total number of parameters. Look at this. How many parameters were there over here? But base case. So 110 million parameters. Look at this. This is nothing but 110 million parameters are there. Okay, fine. Yes, any doubt or any query till this point? If some questions are there, then we can take one or two questions and then we stop here. The second session will be at 3 p.m. Pooja madam will continue that session in which she would explore that BERT and GPT in detail.
Sir,
But
sorry, I
before,
didn't get when to use encoder, decoder, and when only encoder.
okay, fine. Yes, I just forgot that. See, there are three categories of transformers. First one is encoder decoder, in which uh, both the things are there, like encoder and decoder. Both the things are there. Second category is encoder only, in which only encoders are there. For example, uh, we have seen BERT. In BERT, decoder is not there. Only encoder is there, which is used for the efficient representation of input. Efficient representation for input. Example is BERT. Second category is decoder only model, where only decoders are there. Encoders are not there. For example, GPT, GPT-2, 3, 3.5 GPT. All these GPTs comes under the second category, in which only decoders are there. Basically, for generating sort of things, we should use decoder only model. For example, we need to generate one paragraph. Inputs are not that much important. We can directly give the very small part of the input in the decoder itself. Specifically, encoders are not required. So we go with decoders only. This category is known as decoder only model, where only decoders are there. Examples are GPT series. Third category, in which encoders are also involved and decoders are also involved. For example, when input size is very large, output size is also very large, we need to separately process that input by the encoder. We need to separately process, or we need to separately generate outcome by the decoder, in which both the components are required, encoder as well as decoder. So this category is known as encoder decoder. Which are the model which comes under this category? You might have heard of T5, T5, BART,
Not much, sir.
BART.
But I think machine translation would come under this.
Yeah, machine translation would come under the third category. T5, BART are the example. You can
Okay.
explore all this T5 and BART.
Sure. Sure. That's helpful, sir. Thank you.
Okay, so with this, we can stop. Thanks for the patience listening. Thank you.